Section 3.1, prime numbers. We start with the following definition. A prime number is an integer greater than 1 that is divisible by no positive integers other than 1 and itself. Examples: 2, 3, 5, 7, and so on. Note that a prime number is an integer which is greater than 1. 1 is not a prime number. The first prime number is 2. 2 is the first prime number and the only even prime number. Next, a positive integer which is not prime and which is not equal to 1 is called composite. Conclusion: 1 is not a prime integer. 1 is not a composite integer. It's neither. So it's written here. The number 1 is neither prime nor composite. Examples of composite integers: 4, because 4 is 2 times 2. 8, 33, and so on. We start with the following important lemma. Every integer greater than 1 has a prime divisor. Now, you can say, well, it's obvious. If a number is not prime, then it's composite, and we're done. Well, guys, we are not done. Let me give you the following example. 100 is not a prime number because it is equal to 10 times 10. Note that 10 is not prime. So, according to what I just said, it is not immediately clear that 100 has a prime divisor. We have to keep going. We have to apply factorization once again. 100 is 10 times 10, then 10 is 2 times 5. Since 100 is divisible by 10 and 10 is divisible by a prime number 2, 100 is divisible indeed by a prime number 2. So our intuition tells us that indeed any integer greater than 1 has a prime divisor, but if we think how to prove it, the sequence of steps is not that simple. For example, if our integer is big, basically in order to prove that it has a prime divisor, we have to explain our reader somehow that if we keep applying factorization, eventually we will hit a prime number at some step. Question is it possible to write a proof of this statement in a short, clear-cut way? Here is one way to do it. By the way, we will prove this lemma in 2 different ways. In proof 2, we will use induction. But let us start with proof 1. In proof 1, we will use the well-ordering property. We prove the lemma by contradiction. We assume that there is an integer number greater than 1 having no prime divisors. Now, since here we are talking about integers greater than 1, and since we assume that there is an integer in this set with no prime divisors, this set is non-empty. So over here, we are talking about a non-empty set of positive integers. We can apply the well-ordering property. By the well-ordering property, this set has a least element. It's exactly what is written here. The well-ordering property tells us that there is a least integer n greater than 1 with no prime divisors. Now, since n has no prime divisors, and since this n divides itself, n is not prime. Once again, two things that we know about n. Thing number one, n has no prime divisors, and n has the following divisor, n. Since n has no prime divisors, this divisor is not prime. So n is not a prime number. We came up with the following conclusion. A least integer n greater than 1 with no prime divisors is not prime. Since n is not prime, n can be written as a times b, where a is strictly between 1 and n, and b is strictly between 1 and n. Now, please take a look at this. Once again, a is strictly lesser than n. Since n is a least integer with no prime divisors, and a is lesser than n, a must have a prime divisor. Now let us use Theorem 1 from section 1.5. This one. Theorem 1 says that if A divides B and B divides C, A divides C. Let us go back to our lemma. First of all, according to what is written here, by definition of divisibility, A divides n. A is a divisor of n, and A is divisible by some prime number p. So p divides A divides n, therefore by theorem 1, p divides n. Repeat once again. A has a prime divisor. Let us denote it by p. P divides A by this divides n, therefore by theorem 1, P divides n. So n has a prime divisor. We get a contradiction because we assumed that n has no prime divisors. Conclusion: every integer greater than 1 has at least one prime divisor. Any questions here?
If A is less than, why does the fact that A is less than n mean A must have a prime divisor?
Very good question. Please take a look at this. N is a least integer greater than 1 with no prime divisors. Since A is still greater than 1 and lesser than n, it must have prime divisors. Once again, n is a least integer greater than 1 with no prime divisors, the smallest. Since a is even smaller, it must have a prime divisor. You see it?
Yes, thank you.
Next, proof 2. Here we prove the lemma using induction. Let P of n be the following sentence. N is divisible by a prime number. Note that for n is equal to 2, this sentence becomes the following. 2 is divisible by a prime number. This is true because 2 is divisible by 2, and 2 is a prime number. So, step 1, for n is equal to 2, this is true. Step 2, suppose P of n is true for all integers n from 2 through k, where k is some integer greater or equal to 2. By the way, over here we use a so-called strong induction. Strong induction means we suppose that this is true not just for some n is equal to k, but for all integers n from 2 through k, where k is some integer greater or equal to 2. Now, question is, can we suppose it? Yes, because there is at least one such a value of k. By step 1, if k is 2, this is true. So, suppose that n is divisible by a prime number for all integers n from 2 through k, where k is greater or equal to 2. Step 3. Let us prove that this is true for n is equal to k plus 1. That is, let us prove that k plus 1 is divisible by a prime number. Here's how we do it. We distinguish two cases. Case 1. Suppose k plus 1 is prime. Since k plus 1 is divisible by itself and k plus 1 is prime, k plus 1 is divisible by a prime number. Done. Case 2. Suppose k plus 1 is not prime. If k plus 1 is not prime, k plus 1 is equal to ab, where a is strictly between 1 and k plus 1, and b is strictly between 1 and k plus 1. In particular, this means the following. A is greater or equal to 2 and a lesser or equal to k. Therefore, by inductive hypothesis, by step 2, since a is lesser or equal to k, by step 2, a is divisible by a prime number. And now we use again theorem 1 from section 1.5. K plus 1 is divisible by a is divisible by a prime number p. Conclusion, k plus 1 is divisible by a prime number p. We are done. By the way, one remark. The reason why in step 2 we suppose that p of n is true for all integers from 2 to k is the following. Note that since a is between 1 and k plus 1, we cannot really say for sure what is a. A can be k, a can be k minus 1, and so on. Therefore, in step 2, we should suppose that n is divisible by a prime number for all integers from 2 through k. Next, theorem 1. There are infinitely many prime numbers. It's a classical theorem. Here's one way to prove it. We will prove it by a contradiction. Assume to the contrary that there are only finitely many prime numbers. Let us list all of them. So once again, since we assume that there are only finitely many prime numbers, we can list all these prime numbers. Let us denote these prime numbers by P1, P2, and so on, Pn. Here's what we do next. Consider the following integer. This integer, which we denote by Qn, is equal to the product of all prime numbers plus 1. Guys, this portion is very important. Q is not just the product of all prime numbers. Q is the product of all prime numbers plus 1. And we will see in a moment why we need this plus 1. If we do not put plus 1, we will not be able to get a contradiction. And remember, the goal is to get a contradiction. Here's another remark. Note that we can come up with this construction because we assume that there are finitely many prime numbers. Over here, we have the product of all these prime numbers. If there are infinitely many prime numbers, we will not be able to come up with the product of all of them. Since we assume that there are only finitely many prime numbers, we can find the product of all these prime numbers. And then we add 1. Next step. Since this number is an integer greater than 1, we can apply the lemma above, this lemma. By this lemma, every integer greater than 1 has a prime divisor. So, by this lemma, this number has a prime divisor. But note that all prime numbers are listed here. Conclusion: this number is divisible by one of these numbers. Here is what we do next. Let us move this portion to the left. Done. Now, since Q is divisible by one of these numbers, and let us denote this number by Pj. Since Q is divisible by Pj, and this is divisible by Pj because Pj is one of these numbers, both this and this are divisible by same prime number Pj. Now let us go back to section 1.5, Theorem 2. If we replace m by 1 and n by -1, we come up with the following result. If C divides A and divides B, C divides their difference. Now let us apply this here. Since Pj divides Q and divides this product by Theorem 2, Pj divides their difference, but this difference is equal to 1. Since Pj divides the left-hand side, Pj divides the right-hand side. It's written here, Pj divides 1. This is obviously impossible, since no prime divides 1. Any prime is bigger than 1. 1 over prime cannot be an integer. We got a contradiction. This contradiction shows that our assumption is not true. Therefore, there are infinitely many prime numbers. Lastly, theorem 2. If n is a composite integer, then n has a prime factor not exceeding square root of n. Here's one way to prove it. So here's what is given. N is a composite integer. Since n is composite, n can be written as a times b, where a is strictly between 1 and n, and b is strictly between 1 and n. Without loss of generality, we can assume that a is lesser or equal to b. Let us show that a is lesser or equal to square root of n. Here is why. Assume to the contrary that this a is greater than square root of n. But we know that b is greater or equal to a. If a is greater than square root of n, b is also greater than square root of n. Since both a and b are greater than square root of n, their product is greater than square root of n times square root of n, which is obviously n. Conclusion: if a is greater than square root of n, ab is greater than n. Cannot be. ab is equal to n. This gives us a contradiction, therefore the opposite is true. A is lesser or equal to square root of n. Now, since a is an integer greater than 1, we can apply the lemma above. By this lemma, a has a prime divisor. Let us apply theorem 1 from section 1.5 again. Once again, n is divisible by a. A, in turn, is divisible by a prime divisor, according to lemma 1. Conclusion: by theorem 1, n is also divisible by this prime number. But since a is lesser or equal to square root of n, any its divisor is lesser or equal to square root of n, so n is divisible by a prime number. This prime number is lesser or equal to square root of n, therefore n has a prime factor not exceeding square root of n. Folks, we are done with this section. Any questions?
Just the fact that it says n has a prime factor means
Yes.
that the square root of n could be less than another prime factor, but it has to have a prime factor that's less than it.
Well, yes. Think about 14. 14 is 2 times 7. 2 is lesser than square root of 14. However, 7 is not lesser than square root of 14. So here we say that there is a prime factor not exceeding square root of n, but this does not mean that all prime factors do not exceed square root of n. Was that your question?
Yes, thank you.
Any other questions?
Why did we have to use strong induction in that example in class?
Are you talking about proof 2 of the lemma?
I think so. I forgot which one it was, but you said that we had to use strong induction.
Yes. So here is why. Imagine that instead of strong induction, we use normal induction. In step 1, we show that this is true for n is equal to 2. In step 2, we suppose that this is true for some n is equal to k, where k is greater or equal to 2. In step 3, we prove that this is true for n is equal to k plus 1. So once again, if we use normal induction in step 2, we suppose that this is true for some n is equal to k. Correct?
Yeah.
But now, please take a look at this. K plus 1 is AB. The only information that we have about A is the following. A is lesser than K plus 1. Means A can be K, A can be K minus 1, or K minus 2, or K minus 3, and so on. If A is equal to K, we can use step 2, because in step 2, we suppose that K is divisible by prime number. But if A is equal to K minus 1, which is a possibility, we will not be able to use step 2. You see it now?
Yeah, that makes sense.
Any other questions?
Yeah, my question is a little off topic, but so in theorem 2, we said that for any composite integer n, it has a prime factor not exceeding square root of n. So a while ago, I discovered that, let's say you wanted to check that an integer n is prime, you only have to check that it's not divisible by numbers up to square root of n, but you don't have to check it for any numbers greater than square root of n. So does that relate to this, or are they just, is that a coincidence?
Absolutely. That's the whole point about this theorem. Suppose we have an integer. We want to check whether or not this integer is prime. In order to do that, thanks to theorem 2, we have to divide this integer by prime numbers that do not exceed square root of n. We do not go beyond that.
Wait, could you explain how this theorem proves that once again?
If n is composite, it has a prime factor which is not exceeding square root of n. Which means if there is no such a prime divisor, n is prime.
Okay, perfect. That makes sense. Thanks.